Okay, we are starting chapter 3, starting with extrema on an interval. So extrema is either the minimum or the maximum, and we're talking about just intervals today. And obviously the minimum is when everything else in the whole rest of the function is bigger than that point, and the maximum is where everything else is smaller than that point on your interval. So here we have the same interval of the same function, x squared plus 1, from 0, 1 to 2, 5. On the first example here, both endpoints are closed, which means that 0, 1 is our minimum because it's the smallest point on the interval, and 2, 5 is our maximum because it's the highest point on our interval. For the second one here, it's still the same points, 0, 1, and 2, 5, only at 2, 5, it is an open point. So our minimum is still 0, 1, but we actually don't have a max because your line is going to get progressively closer to 2, 5, but it's not ever actually going to touch it, so we can't say that the max is really close to that. We just say there's no max at all. And so the same thing goes for the third one, except this time there's no minimum since it gets really, really close to 0, 1, but never actually touches it. And we have 2, 5 as our max. So that's how those endpoints are affecting the minimum and maximum. So if we have a continuous function over an interval, then it has over a closed interval, so it has to be closed on both endpoints, then we know that your function is going to have both a minimum and a maximum on that interval, which is pretty much what we just showed by the first part of that top example. All right, so we have the function x cubed minus 3x squared, and we're not doing much with this problem. It's just saying that there's a relative maximum at 0, 0 and a relative minimum at 2, negative 4. Just right here. The function looks something like that. So obviously that is a max, and the bottom one is a min. Now they're called relative because there's not over a specific interval, it's just the function overall. So that's when it's called relative. It is absolute maximum or minimum if it's over an interval. If we have an open interval containing c, then it's relative. So if it's an open interval instead of that closed interval where we had absolute, this is going to be a relative if it's an open interval. So let's find the value of the derivative at each of the relative extrema shown. So it's going to be easier on this one to multiply through the top and divide both terms by x cubed than do the quotient rule, but you can certainly do the quotient rule. F prime is 81 x to the negative 4th, and if you plug in 3, it's actually 1. We are going to skip the absolute value. Sine of x, let's find the derivative of sine of x. It's cosine x. F prime of pi over 2 is 0, and f prime of 3 pi over 2 is also 0. Okay, let our function be defined at a point c. If f prime of c is 0, or if f is not differentiable at that point c, then c is a critical number. So what does it look like if you have a non-differentiable? You're going to have the function come up to a sharp peak like that at your point c. This is where it doesn't exist. And f prime of c is equal to 0 when you have a horizontal tangent at a point, so like right here. See, you could draw a horizontal tangent in at that point. That's when we have a 0. So that's what you're looking for. You're looking for either where a function is equal, a derivative is equal to 0, or where it doesn't exist for those critical numbers. If your function has a min or a max at a point, then that point is a critical number. And as you could see in this up above example, that was a relative maximum when you have a 0 for the slope. That's a horizontal tangent. Horizontal tangents always occur at mins and maxes. Okay, so the rest of the section, we are going to follow these instructions. To find extremum of a continuous function, we need to find the critical numbers. So we're going to take the derivative. This is when the derivative is equal to 0, or it doesn't exist again. and then we're going to evaluate the function, so the original function, add all of those critical numbers, and you're going to evaluate the endpoints, put those endpoints into the original as well, and then whichever one is the smallest is your min and the biggest one is your max. Find the extrema of 3x to the fourth minus 4x to the third on our interval from -1 to 2. So the first thing we need to do, according to those instructions, is to find the critical points. Find the critical points by taking the derivative. 12x to the third minus 12x squared. So we're finding where it's equal to 0. We're going to factor this. And x equals 0 and x equals 1 are our critical points. So what we're going to do at that point, because it's not going to ever, the derivative is never going to be undefined, so we just know that 0 and 1 are our critical points. We also need to evaluate it at the endpoints. So I think the easiest way to organize this is to make a little table. Endpoint, we're going to use the critical numbers. And we have 2 of them, so there's going to be 2 in the middle. And we also need to evaluate the right endpoint. Left endpoint was -1, critical 0, 1, and the right endpoint was 2. So we're going to plug all those in. F of -1, so that's plugging it back into the original, is 7. F of 0 is 0. F of 1 is -1. And F of 2 is 16. So now what you're looking at are the function values there, 7, 0, -1, and 16. You're trying to find which one is the smallest and which one is the biggest. The smallest one is 1, -1. That's your minimum. And 2, 16 is going to be your maximum then. That's the biggest function value. All right, so let's do the next example. Find the extrema. So we need to find the derivative. 2 minus 2 over x to the 1/3 or x to the -1/3. The critical values occur when f prime is equal to 0 and when f of x doesn't exist. That happens at 1. That's going to be when x is equal to 0 and f prime doesn't exist at 0. So those are our 2 critical points. And then we also need to evaluate the endpoints, -1 and 3. And if you find critical points that are not within your interval, you don't have to use those. We're just using the ones that are inside our interval. And so far, all of them have been inside of our interval. Okay, so we start with left endpoint, and we have 2 critical numbers. And a right endpoint. Left endpoint is -1. I always go in numeric order, but you don't have to, just to make things consistent. Okay, f of -1 is -5. F of 0 is 0. F of 1 is -1, and f of 3 is 0.24, -0.24. So you're looking for which one is the smallest and which one is the biggest. Well, our smallest, it's right here, min, -1, -5, and our max is at 0, 0. And that's that. Okay, one more example. We're finding the extrema of a trigonometric function this time. So it's the exact same process. We need to find the derivative first to find the critical points. F prime is equal to 2 cosine x minus 2 sine 2x. That's the chain rule inside of the cosine 2x. And then we need to find where that would be equal to 0. That's never going to not exist when you have cosines and sines. So I would just graph it to find the zeros. Equals 0 at x equals pi over 2, 7 pi over 6, 3 pi over 2, and 11 pi over 6. You could also use the decimal approximations of those values. So we have to use those, and those are the critical points just within 0 to 2 pi, since that was what our interval is. And we have 6 points to evaluate now. Critical number, critical number, critical number, and the right endpoint. So in numeric order. Okay, now I'm just going to plug each one of those into the function. Here I get -1, 3, -3 halves, -1, -3 halves, and -1. These are all of our function values every time. If you use the decimal approximations instead of the exact pi answers, you will get probably really close to those, but you might not get exactly -3 halves. Just be really close. So now we're looking for whichever one is the smallest and whichever one is the biggest. Well, the biggest is easy to find. That's the 3. Max at pi over 2, 3. And we actually have 2 that are the smallest. So we can, in fact, have 2 minimum. 7 pi over 6, -3 halves, and 11 pi over 6, -3 halves. And that's actually it. So that's section 3.1.